Okay, in this video I'm going to take you through catalysts, how they work, some examples, and calculating activation energies and heats of reactions. So basically, what do catalysts do? The primary purpose is that they lower the activation energy, and they do this by offering a different reaction mechanism to proceed from reactants to products. You still have the same reactants, and you still have the same products, so the heat of reaction is going to be the same, whether it's downhill like this or uphill. And think about it as a hiking trip, all right? So you want to go from here over a mountain over there, okay? And there's two hiking paths. One will take you right over the peak of the mountain, which has a high activation energy. That's essentially no catalyst. And then there's another hiking path which will, meander around the mountain in a different way, but it won't go as high. And so potentially you can go faster through the path that doesn't go as high in altitude, okay? So if you lower the activation energy, remember that the rate constant is going to be higher, which means the reaction rate is going to be faster. So this comes from the Arrhenius equation. Now, there are two types of catalysts. There are homogeneous catalysts, which are dissolved and dispersed in the solution. That can be aqueous solutions, for example. That can be biochemical catalysts or gas phase catalysts. And heterogeneous catalysts are usually a solid, maybe a molecular sieve or a metal gauze or a solid powder that's added to a gas or various liquids. So let me show you a couple of applications before we jump into this. First off, we have hydrogenation. So margarine is made by reacting vegetable oil, which is this triglyceride, which is a reactant, with hydrogen gas, another reactant. And these normally don't react at standard atmospheric pressures and temperatures, but if you add nickel as a catalyst, these can react and you'll form what's called partially hydrogenated vegetable oil, or margarine, okay? And that's a very big application, hydrogenation. The textbook has a little figure here about how nickel actually works. Nickel is a metal surface, and hydrogen can absorb onto the surface of it, and so can the alkene, which is the ethylene or the olive oil or something like that. And then basically the nickel will react with the hydrogen and deliver one hydrogen, and so they basically add on to the organic molecule to give you the hydrogenated product. Another biggie is Ziegler-Natta catalyst. This is prepared by mixing titanium 4 chloride and triethyl aluminum, and they don't really know what the active form of this catalyst is per se. It's a mixture of different oxidation states and structures and so on, but it's very important because it's used to make polyethylene and polypropylene and other polymers, okay? So on the bottom left, we have polypropylene, which forms everything from your plastic buckets to ketchup bottles, shampoo bottles, and things like that. And polyethylene is used, for example, in cutting boards, as well as milk jugs and plastic shopping bags. So these are very important polymers that are made on ton scale. And again, the defining feature of a catalyst is that they make a reaction faster, but they are not involved in the overall chemical reaction, okay? We're taking organic materials to other organic materials, and the titanium and the aluminum and so on are not being incorporated into the polymer plastic. A third example here is alcohol dehydrogenase. On the right here, you can see how alcohol is metabolized. So if somebody drinks alcohol, it is first metabolized to form acetaldehyde. Acetaldehyde gives the headache feelings, the hangovers, the nausea, and so on. And then the acetaldehyde is further converted to acetate, where that's excreted from the human body. On the left, I have a little video. First, I want to show you the zoom in here for alcohol dehydrogenase. So we've got this NAD analog here. It's a cofactor that binds into the alcohol dehydrogenase. We've got a zinc atom here in kind of orange, and there's a couple of side groups on some proteins that hold this zinc atom in here. And then we've got this small little thing, ethanol. So if we kind of zoom out here slowly, you can see that ethanol is very small compared to this huge, polypeptide, which is a huge biochemical catalyst. So there you have it. Many different catalysts within the human body are proteins, and these are very large, complicated machines that have a very specific function. Here you're going to convert ethanol to acetaldehyde. All right, now that we've seen some examples, let's take a look at what we need to be able to do. So this is example 1215 from the OpenStax chemistry textbook. We have two reaction diagrams here for the same reaction. One is without a catalyst and one is with a catalyst. And we're supposed to estimate the activation energy for each process and then figure out which one involves a catalyst. So this is a great review problem. First of all, remember that the activation energy is defined by the top peak in the energy landscape, and we take the difference of the starting materials, okay? So that's defined as the activation energy. And we can read this off the graph, and we can see that it's about 26 kilojoules when you do the math, okay? So the reaction on the left has an activation energy of 26 kilojoules, and we can do the same analysis on the reaction on the right. So the tippy peak is here, and we can take that difference and recognize that as the energy of activation. And when you do the math, it's about 20 minus 6, which is 14 kilojoules per mole. So on the left, we have an activation energy of 26 kilojoules, and on the right, we have an activation energy of 14 kilojoules. Now, the reaction on the right is catalyzed because it has a lower activation energy. It's going to make that one a faster chemical reaction, okay? Here's another problem, problem 80. It says for each of the following pairs of reaction diagrams, identify which of the pairs is catalyzed. So by a similar analysis, we want to take a look at the reaction on the left, and we want to figure out where is the highest peak in the overall energy landscape. It's the first peak, okay? And we want to take the difference between the starting materials, and that's going to be the activation energy for the whole complete reaction, okay? And when you do the math, this chemical reaction on the left has an activation energy of 42 kilojoules per mole. We do the same thing on the right. We can see the tippy peak has a particular energy. We can take the difference between the starting materials, which is on the left, very left always, and the activation energy here is also 42 kilojoules per mole. So what this means is that both reactions have the same activation energy, which is quite high, so they're actually going to be the same rate and the same speed, okay? But if you look very carefully at these chemical reactions, you can see that the second peak on the right is actually a little bit lower, okay? And a catalyst is designed to lower the activation energy. So on the right, we have a catalyzed reaction. On the left, we have an uncatalyzed reaction. Now, it turns out that we're speeding up a step in the reaction that's fast anyways, so it's not going to make it the overall reaction any faster. So this is a very interesting example, okay? Now, I want to make a note about calculating the heats of reaction from these reaction coordinate diagrams. Now, the thing to remember is that catalysts do not alter the delta H of a chemical reaction, because you're going from the same reactant to the same product in either case, and so the heat of reaction is just defined based on the relative energies of the products and reactants. So what you want to do is locate your products and draw a line, okay? And then you want to take the difference of products minus reactants. It's always the energy of the products minus the energy of the reactants to get the delta H. Here it's an uphill reaction because the starting materials are lower in energy and the products are higher in energy, okay? So the heat of reaction is 12 kilojoules per mole for both of these chemical reactions. It's positive 12 kilojoules per mole, all right? So we say that both of these reactions are endothermic. Remember, if you have a positive value, it's endothermic. And we also say that it's uphill, right? Because the starting materials are lower and you're going uphill to the products, okay? Uphill. Sure, you're going over some peaks and stuff, but at the end of the day, you're going up to a higher energy, okay? And the delta H for that process is positive 12 kilojoules. So I hope this gives you a brief overview of how to calculate activation energies, enthalpies of reaction, and understanding a little bit more about how catalysts work. Thanks for watching. Please like, please subscribe. Have a great day.